block, and he's going to be talking about how to compute ranks of tensors.
Thank you. It's a great pleasure to be here. I'll talk about this joint work, recent work with my advisor Alessandra and also Joachim on how to use these multiplication tensors of algebras, which Mate kind of introduced yesterday, but I will very slowly and softly talk about them using how to compute ranks using them. So, okay, maybe I wanted to start a bit too low, but I will very fast because I wanted to start with the rank of a tensor. So, okay, the rank of a tensor generalizes the rank of a matrix, but which notion of the rank of the matrix are separate equivalent ones. The one that works for multilinear algebra is the last one, so the smallest integer are well, the matrix is a linear combination of rank 1 tensors around matrices, and this is the one that realizes the tensor. And today we're interested in the symmetric setting. So we have a symmetric tensor, and we want to compute the symmetric rank, which is the smallest r, such that f is a sum of rank 1 symmetric tensors. Once we fix a basis, this problem can be made very explicit. Namely, we have a homogeneous polynomial, and we want to express it as a sum of powers of linear forms using acylinear forms of the count. For example, the monomial xy have wording rank 2. It's the rank 2 decomposition using the binomial formula. It's not a power of a linear form, so we can do better than this. Whereas x to y have wording rank 3, then this is the rank 3 decomposition. It does take a bit of work to show that you cannot really do better than this. So some context about this problem. This has already been said. The set of tensors of most are. It's not an algebraic variety, and there's not a set of polynomial equations that can give me a test. And so we need to take the closure of this set. It's for the rank almost R. And there's this very big result in this direction from the algebraic geometry point of view. The Alexander-Kirchhoff's theorem, which is about the dimensions of sequence of coordination varieties, but in particular, it computes or it determines the rank of a generic polynomial. Although it still doesn't really help me to compute the compositions of a particular polynomial. And years ago, Bernard Morin and co-authors designed this method that can compute the working rank and the compositions of any polynomial. It seems that the Casanova amount of regularity is really a very good indicator of how well this method can be. Keep in mind that this is an maybe hard problem, so having a method that can work perfectly well for all cases is almost by definition impossible. But under this bound, for which I think Enrica today will also say a few more words, everything can be done efficiently and using just linear algebra. However, this regularity doesn't really depend on how simple the polynomial is. You can have a polynomial with low rank, low number of variables, low degree, and still not be able to work this out. And another interesting calculator that comes into play here is that, as Alessandra and Daniela realized a while ago, this algorithm is especially about computing local Gorenstein schemes of a polynomial. So it can be used to compute the cactus. I will find this later. And what we're gonna show today is what we've been doing in this project, which is to understand all this method in terms of multiplication tensors of inverse. Okay, let's go with the definitions. Definition is a polarity or contraction. The setting is quite general. We have an algebra, and for every element P, we consider the multiplication by P map, and we take the transpose of this map. So this we know by basically linear algebra that it's going to be a functional and another functional, which acting on P returns the product lambda 5 times Q. In the moment theory. For the Hankel operator, so if lambda is a functional, this construction is an operator. And so it's a linear map. You can put it in an infinite matrix where each of the entries will be the moment associated with the monomial. And if we fix some basis, so the monomial basis and its dual, this can be seen as a scale partial differentiation. Again, I think Daniele in his talk already for this formula, this can be done by direct computation. And in this A-module structure, we are interested in the annihilator of an element. So will be the set, so given a homogeneous polynomials will be the set of polynomials that kill my f under this subtraction action. Again, if we think of this as derivation, we will have a polynomial, and then we think of all the differential operators, polynomial differential operators, that will manage my polynomial. And in this moment theory, this will be the kernel of the moment matrix. And we're going to say that an algebra is Gorentzian if this A structure of the dual gives us an isomorphism. So the dual is a rank 1 A module, meaning that it's generated by a single element called the dual generator. But we have a very good understanding of how these algebras look like. Namely, there's a Macaulay correspondence. So that every local Archimedean algebra, Gorentzian, is isomorphic to the quotient of the polynomial ring by the annihilator of some polynomial. And for the people who like theory, when I say Gorentzian algebra, you should think as the polynomial ring quotient by the kernel of some polynomial. Finally, we're going to say that the scheme, objective scheme, is a polar to F. The ideal of the scheme under some embedding, or some fixed embedding, is contained in the annihilator. And this definition here is here in the Apolak dilemma, which says that it bridges these two compositions with this polarity theory, and says that a polynomial can be expressed as the sum powers of the forms L1, L2, all the way to LR, if and only if the ideal that this linear forms define, so I should think of the linear forms as points in the projective space, is contained in the annihilator. And in this annihilator, we can also look for not only smooth points, not only reduced schemes, but also any type of scheme we can find. We're going to call the cactus rank the minimal length of the scheme. So this generalizes the wording because the length of a set of points is just the cardinality. The length of a zero-dimensional scheme is a bit more technical, but it's the one that generalizes. So the annihilator really is like a bag where I can put my hand and look for things. I cannot really see inside. And so with a hand, I can touch things and then I can take out all the compositions of the tensor. Sometimes I think I have a decomposition, but then I take it out and it turns out that it's some point with an extra structure. But the point here is that I can only do that after I take my hand out. This is a very dummy way to picture this cactus barrier that Matti was talking about yesterday. This is the state of the art. So inside the annihilator, we're looking for things, and in most cases, we can compute the things we can find inside are going to be the desired one, because we're in the compositions, but in general, we're going to find some non-reduced thing, and we're going to talk about that. Next, we move with these structured tensors, algebras. We need a technical definition first, which is conciseness. I think it has also appeared during this week. We're going to say that a tensor is concise if intuitively we cannot put it in a smaller tensor space. For example, this tensor here is not concise because I'm writing it in a 2x2 tensor space, but it can actually be done in 1x1 space. This is 2x1, but it's really a 1x1. For the trained eye, this is a rank 1 tensor, so it cannot be concise unless it's written trivially. And for symmetric tensors, so homogeneous polynomials, this just means that I'm really using all the variables I have. This is the minimum of conciseness. So this x plus y cubed minus z squared is not concise because I can somehow, up to change of coordinates, linear change of coordinates, write it using just 2 variables. But as you can see, like, if something is not concise, then you just have to write it properly. And we're also going to consider some action of change of coordinates. So we're going to say that if I have 2 tensors in different vector in tensor spaces, that the T2 restricts to T1 if I can find linear maps between the corresponding vector spaces, so that the induced image and then this map tends one to the other. Again, in the symmetric case, this picture is simplified. It's just a linear change of coordinates between the tensors. Okay, now we have an algebra, and we're working over finite dimensions. So we ask this algebra to be Artinian, meaning that in this setting is going to be a quotient of the polynomial ring, which has finite dimension as a vector space. So now we have a vector space of finite dimension. And we consider the map that takes a collection of D elements in A and sends a product. This is linear in each of the factors due to the properties of multiplication. So this is a multilinear map to a tensor. And because of the way that we write tensors using duals and so on, the first D factors of this tensor are going to be dual A. The last one is going to be plane A. This is hopefully a little later. And an important remark is that this tensor is always concise, because intuitively, every element of the algebra plays a role in the multiplicative structure, at least multiplying itself by 1. So the tensor, which should contain all the information of how the elements of the algebra multiply with each other, every element should appear in this tensor, so this tensor is concise. Let's see an example of this. We have a very simple Artinian algebra, K of x cubed. So the residue class of any polynomial will not contain terms higher than x squared. And so a basis for this algebra is 1x and x squared. And multiplication, the structure tensor, or the tree, should reflect this multiplication table here. So 1 times 1 equals 1, 1 times x squared is x squared, but x squared times x will be x cubed, which is in the ideal, so 0. And this is what this tensor here means. Again, we should think of this as 1 times 1 equals 1, 1 times x equals to x, and so on. For every Artinian algebra, we have a source. Artinian algebra are big sort of size tensors. And if we restrict to the symmetric tensors on the your right hand side, on the left side I have Artinian coordinate algebras. Why is this? Because remember that A is isomorphic to A star as an A model, so it particularize a vector space. And so the structured tensor, which again was living in D times copies of A star, and the last one was an A. Now the last one I can put it isomorphically to the A star. And so I have a new tensor, which I'm going to denote this the S, that leads in A star to the tensor power. And this S here stands for symmetric, because as a multilinear map, it would take D plus 1 elements and return lambda, where lambda was the dual generator of the coordinate algebra. Lambda applied to the product of both. So since this algebra is commutative, I can just swap the elements in here, and it gives me a symmetric tensor, because the result is good. Let's verify this with the previous example. So again, this was the algebra we started. Now I can unmask it and see that So that this is a constant algebra because it's the annihilator of x squared. Why? Because if I derive x with x squared, I get x. If I derive it two more times, I get 0. One more time, the end of it. And this isomorphism would send 1 to 1 contracted with x squared, or x squared. This is just x squared, equal x to x contracted with x squared. And the x will just give me x. And so the tensor here, which is the same one I wrote before, we should map it to the corresponding symmetric tensor with just removing the last factor in each of the summands for the image under this isomorphism. And now you can help me verify with me that this is indeed symmetric. In the first one, we have 1 x squared. Here we have 1 x squared 1, x squared 1 1. So we have all the 3 permutations. And the other 3 would give the other summand. We usually, like we said, what the big spaces, symmetric tensors are identified with homogeneous polynomial. In this case, we can think of it as this cubic cube. Okay, so how can we use all this machinery to the problem of computing ranks of tensors? We're going to start with a very, very innocent observation that starts with computing the structured tensor of k to the m. So the algebra that is pretty much multiplicative as simple as possible because the points on different k's don't interact with each other. So if I fix the canonical basis, this element times this element is 0. So pretty much the only thing that can be in the structured tensor are pure powers of the variables. So the structured tensor, or the V, is this polynomial here. This is concise, like we said. And this is a rank n decomposition of this tensor. And you cannot really do better because for concise tensors, the rank is at least the number of variables. So the working rank of the polynomial is exactly equal to m with this decomposition. And conversely, if I have a polynomial with minimal working rank, so it has m variables, and I can write it as a sum of m powers, as a sum of powers of linear forms using m linear forms, linearly independent, then I have a map that sends this xi to li that clearly gives me an isomorphism between these two tensors. So this is just saying that a polynomial has minimal working rank if and only if it's isomorphic to the structured tensor of k to the m. It's a plain bijection that is quite innocent, which doesn't work for higher ranks because if R is higher than dimension B, where the vector space of F is concise, then the same game will only give me surjection because now the LIs cannot be all linearly independent. But this still shows that F has working rank R, even only if is a restriction of the structured tensor of k to the m. K to the I, where R is the 1. And it turns out that this statement generalizes to the non-reduced case as well. So let's go over this statement slowly. We have n plus 1, the number of variables, and f a concise symmetric polynomial, and z that is a scheme which is 0-dimensional, and Gorenstein. One thing I didn't mention is that we can just restrict to the Gorenstein case for the cactus because it's a result by Bushinsky that the cactus will always be computed by Gorenstein schemes, so we can just focus on them. And the statement says that the ideal of Z is contained in the annihilator, even only if we can find this restriction between the structured tensor of A and B, so that one is the polynomial is the image of the other. And so in particular, the polynomials that have minimal cactus ranks, so cactus ranks equal to the number of variables, are the structure tensors of the Archimedean algebras. And okay, the last minutes, I'll show how we use all this in an example. I'll have to put a lot of things under the rack, but feel free to ask in the questions. We have some polynomial. Oh, I thought I fixed the spacing. We have a polynomial which is a bit large. We can find some polar schemes of degree 4. And what we do is we extend f to another polynomial that has 4 variables. And so f has 3 variables. We want to look for schemes of degree 4. So we have an extra variable. So we put this g, which is f plus terms that contain this new variable. And now we impose that this g is a multiplication tensor. So note that if this were the case, so if g is a multiplication tensor, then there's a restriction from g to f, which is just sending this new variable to 0. And therefore, by the previous result, this would give me that there is a scheme of rank of degree 3. So scheme of degree 4. How do we impose that G is a multiplication tensor? Well, first we fix a basis. Once we have fixed a basis, some of these coefficients will become numbers because this x3 will correspond to some of the elements, one of the elements in the basis. And once I have this, I can compute what they call the multiplication matrices by the variables in the algebra. So we're targeting this algebra here, which is x1, x2 quotient by some ideal. I can consider the map that sends one element, that takes one element and multiplies it by x1. This is a finite vector space, so finite dimensional vector space, so this is going to have a matrix. And this matrix can be read from the tensor. So notice here that some of the entries of these matrices will be parameterized by the coefficients of the tensor. And now we kind of reduce this problem to border basis theory. And we impose the commutation of these matrices. Intuitively, these are commutative algebras, so these matrices should commute. Let's put it this way for now. And in this case, this would be a polynomial system with respect to these variables with a unique solution in this case. And once I have these multiplication matrices, basically the problem is over because I can know what the algebra is, I can compute the ideal, I can compute the Hilbert function if I want in this case. So this would the matrix would look like if I put values back. In this case, it would correspond to just 4 points, and these 4 points give me this decomposition of it. Okay, I will quickly wrap up. What we see today is that for every affine algebra, we can associate a tensor that is concise and symmetric, even only if the algebra is Gorenstein. That all this geometrical polarity can be understood in terms of these multiplication tensors and their restrictions. In particular, that the cactus is minimal when my tensor is a multiplication tensor. And otherwise, by creating restrictions, I can maintain all the other elements of rank R. And finally, we can build an algorithm that makes an extension by variables of the polynomial to compute the Warren and the cactus. And that's it. Thank you very much.
Quite a very nice talk. Are there questions?
The what's her? Yes, it suffices to find a solution. So one implication is clear because the algebra is commutative, so this means you need to commute. The other one is also a necessary condition. Yes, there's also an open condition which I didn't mention, but essentially.
Well, it's not really like that. So like your algorithm kind of finds all possible cactus schemes, right? So you have equations for the cactus BSP of the
Yes. Yeah. Very kind of unpractical way, but yes.
So these equations are not
no, not necessarily.
What about the dimension of variety?
No, I mean this is an excellent question, but so far we I mean in this example I chose it so that it was unique, so I knew what I was aiming for. But in general, this can get a very complicated polynomial system, also with some open conditions that are difficult to deal with. So it can get very
But if you are generic on that component of the cactus variety, you have finite demand. This is generic on 1 to 4. Right? And then you have another that is like a
the cactus variety is, from what I know, not very well understood.
You can lift with random coordinates. Points. So this is a kind of dimension extension from tensor. So you can take random coordinates, new variables.
And then you find one solution if there's a solution. But then you can visit more solutions.
So it means you have a lot of people.
Yeah, depends on the question. Yeah, depends on the question. If you wanna get a lot of new equation in one solution, then you go for around. If you look in the equation that we were saying, that there's something.
Do you have an example where you miss solutions like this?
Right, so this is another important point. Thank you for bringing it up. So if you fix a basis, you might miss algebras for which this monomial set is not a basis. So in theory, you should exhaust all the possibilities. This is really a bottleneck of this. We have so in this original paper by Bernard and co-authors, they say that this monomial set has to be of a particular shape, it has to be connected to one, so you can build a set. Then Daniela Sandra said that it has to be closed on the division as well, containing all the variables, so the choice is reduced. We show that you can even go further than this and reduce the number of options. But yes, in theory, before discarding one particular part of the rank, you should exclude all the possible bases.
The principle that we made one. Maybe just a quick question. So thank you for the presentation. It was very clear. Maybe for the sake of clearness, you swap under the concept of the open condition. So I would like to see what is the open condition.
Yes. So the open condition would be that this G here is not in degree 4. I would make the construction with x0, and I would impose that this is concise. And this is exactly the same condition as asking for the non-vanishing of the determinant of the angle without basis.
which is essentially like you lose your path. All comes recorded.
Yeah. You have to be very unlucky to choose the wrong one.
And also, you say like variance. Is it because maybe that just by adding one you don't succeed and do may need to create multiple new ones.
Yes, so the number of variables you need to add is the difference between the ones you have and the rank. So in this case, I just added one because I have 3 variables, wanted to look for 4, let it be 4 schemes.
So, let's speak one more time.